Good morning, all. So in the last class, we were looking at the theorem that regular languages are equivalent to regular expressions. That is, a language is regular if and only if there is some regular expression to describe it, right? So we sort of split it into two parts. One is if you have a regular expression, then the language that it is describing will be regular. So that we started proving as lemma 1. The second lemma will be if you have a regular language, then there will be some regular expression describing it. All right. So the first lemma we started proving by considering the 6 different cases of regular expressions. You remember regular expressions can be covered using 6 cases, 3 primitive cases and 3 complex cases. So if we can show that each of these primitive regular expressions can be converted to or the languages being described by each of these primitive regular expressions like this. Yeah. So these are the 6 cases, right? Each of these cases describes a particular language. Now it only says that each of these regular expressions describes a particular language. It does not tell us whether that language is regular or not. So we take these 6 cases, we look at the language being described by each of these cases, and we will build an NFA for each of these cases to prove that each of these languages is a regular language. Okay, so we take the first 3 primitive cases. We looked at the first 2 cases so far, that if the regular expression is just A, then the language that is being described by this regular expression is a singleton set with a single string A. Now, to prove that this language is a regular expression, we need to build an NFA for it, for this one, right? So that's what we did. So that proves that this language is a regular language, right? Because the language is regular if there is a finite automaton accepting it, recognizing it. Okay. Similarly, we take the second regular expression, that is epsilon. The language that is being described by epsilon is again a singleton set with epsilon as the only member. And then we build an NFA that recognizes only epsilon. So this proves that this particular language, this particular singleton set is a regular language. All right. So now let's prove for the remaining cases as well. The third case is the regular expression is a null set, right? Then the language of this regular expression is also an empty set, right? And the following NFA recognizes L of R. So what will be the NFA? Start state. That's it. Yeah, there's only one state, start state. There is no final state and no other transitions. So that machine will basically accept nothing. That's it. This is the NFA. Okay. Now let's also formally describe it. So formally, N is a 5 tuple where the set of states has only one state, Q, and sigma delta start state is also Q, and set of final states is empty set. Okay, where delta RB equal to null set for any R and B. Okay, so we sort of proved that the 3 primitive regular expressions A, epsilon and phi, the languages represented by these regular expressions are regular languages. Now we need to prove for the complex regular expressions, that is R1 union R2, R1 dot R2 and R1 star. For this, we need not put much effort because in the theorems where we proved that regular languages are closed under each of these operations, we already showed how to build complex NFAs. Like if you have to build union of two regular languages, you need to perform how to combine two NFAs. That we showed. So same thing. Now these primitive cases are proved. You need to use similar constructions as you used in the theorems to construct complex NFAs for these complex regular expressions as well. That's all. So we won't explicitly show that again. We'll just mention that you can refer to the previous theorems. So R1 union R2, R1 dot R2, and R1 star. To prove this, we use the appropriate NFA constructions demonstrated in the earlier proofs that the class of regular languages is closed under regular operations. All right. So we need not again go into step-by-step construction. Like if you know R1 as a primitive regular expression and R2 is a primitive regular expression, you know their languages are regular, you know they have their corresponding NFAs. Now to perform R1 union R2, you just follow the same construction as you did when you proved that union of two that regular languages are closed under union operation. So the way you combine NFAs there, same thing you will do here also for concatenation, union, star, everything. Okay. So that ends the first part of the proof of the theorem. Okay, that is the first lemma. So now that we are done with proving the first lemma, let's look at some examples. Okay, so convert the regular expression AB union A whole star to NFA. So we need to sort of do this step by step. This is a complex regular expression which is made up of atomic regular expressions. So what are the atomic regular expressions in this? A, B and A. But AB itself is again a complex regular expression. Yeah, A and B. So this regular expression involves all the regular operations, concatenation, union and star. Where is concatenation? So this A is concatenated with B, and then this regular expression has a union with A, and then this entire regular expression has star. Okay, so all the three operations are shown here. So you should first start with the most primitive regular expressions, that is A and B, and then perform concatenation of AB, and then perform union of AB with A, and then perform star of this entire regular expression. Okay, so if such a question is given to you, you have to show each step, starting from the primitive regular expressions. So first let's show it for A. It is a simple two-state NFA. Where from start state on A, you go to the final state. Okay. And then similarly for B, now AB. AB is concatenation of first regular expression with the second one. So you need to sort of concatenate first NFA with the second one. So how do you do that? Yeah, so concatenation, if you remember, if you have two NFAs, you have to have epsilon transitions from all the final states of the first machine to the start state of the second machine, and convert all the final states of the first machine to non-final states. So both these conditions are important. You need to have epsilon transitions from the final states of first machine to start state of second machine. That's one condition. Second one is convert all final states of first machine to non-final states. Both these are important. So this is for A. This is for B. So this final state of first machine, I converted to non-final state. Now I link this final state with the start state of the second machine with epsilon transition. Okay, you could as well write like this without epsilon, but you should not write like this when this question is asked. When you are asked to show step-by-step procedure of constructing it, even this will come later after when you're trying to optimize this, but this will come first. The epsilon version will come first. Then how you optimize, there are various ways. So you should not show only this by skipping this. And it's okay even if you don't show this at all, but this you have to show the epsilon transition, because concatenation involves transition. Okay, so if you're asked to show step by step, you have to show this step. You cannot skip this. Okay, so AB is done. Now we need to do AB union A. So let me copy AB and A. How do we combine them? Yeah, so you create a new state and add epsilon transitions from the new start state to the previous two start states. That is how you perform union of two NFAs. So I create a new start state, and from this I add epsilon transitions to the previous two start states. Okay, so this is AB union A. Now finally AB union A whole star. So how do you perform this one? How do you perform star operation? The same start state will become accept state. Yeah, you need to add a new start state which is also an accept state. From that you need to have epsilon transitions to the old start state, and also you should have epsilon transitions from the final states to the old start state. So let me show it. So first let me add actually epsilon transitions from the final states to the current start state. And now let me add a new start state which is also an accept state with epsilon transition to the previous start state. Okay, so this is how you perform star operation. All right. Okay, now this is step by step how you convert any regular expression to NFA. But suppose you were given this regular expression and directly asked to build an NFA. Then how will you, then what will be the NFA? Just try it and let me know. So build an NFA which accepts the language AB union A whole star. So build it and let me know. Is anyone done? Quickly. No one is done. Yeah. Two states. Both are accept states. Okay. On A it goes to second state. Okay. Self loop A and B. Okay. That's it. Is this correct? Why? And it will even accept B also. Oh, sorry. Sorry, it will accept A, B star, not only B. You see, when we mean AB union A whole star, it's like you can imagine there are many places, and in each place there are two options, AB or A, right? So AB or A any number of times. So you can have strings like AAB, and then AB, and then AAA any number of times. A's can come any number of times, but for every B, it should be preceded by an A. Yeah. First one. On this. Okay. Okay. Sorry. First accept. So is this correct? Okay. Seems to be. Okay, we can simplify this further. Um, okay, so this is one other way of simplifying it. So this will accept any number of A's followed by B, again BA. It can be any number of A's and then any number of AB's. All right. This is simpler, but there is another version which is more closer to the expression. So let me show that as well. Okay, so first we have A. So A will be accepted and AB will also be accepted. Now we want to have any number of A's or any number of ABs. Okay, so I will add an epsilon arrow here so that it will come back for any number of A's. All right, and I will also add an epsilon arrow from here so it will come back for any number of ABs. Now it's not necessary that you should have only series of ABs or series of A's. You can have a mix of A's and ABs, right? So this will handle both the cases. So after getting an A, you come back, now you can get an AB. Or after getting an AB, you come back, now you can get an A, right? So simple thing is you can get A or AB and you come back and you can again get A or AB. So this is like each place is being captured here in one in a direct one-to-one scenario kind of a thing. So A will also be accepted, AB will also be accepted. After reading A also it can come back and it can get an AB, or after reading AB also it can come back and it can get an A or AB, right? So this is more closer to the expression. All right. So there is no one answer. There can be more answers as well. But the thing is, it's only through practice you will arrive at the right answer. There is no one single algorithm using which, I mean, the previous one is an algorithm. Like this is actually the one what we saw actually. This is an algorithm to convert any regular expression to NFA. But if you don't follow the step-by-step procedure, if you want to directly come up with the NFA, there is no particular algorithm. Okay, if you follow the algorithm, you will get such complex machines. Okay, so it's more about practice. So let's move ahead. All right. So now, before we move on to the second lemma, so far we are done with the first lemma, that is given a regular expression. How do you build an NFA out of it? Now we will move on to the second lemma, that is given an NFA, how do you convert it to a regular expression? All right. So before we start the second lemma, first let's look at some examples. So if this is my NFA, what is the equivalent regular expression? Just A. We just saw that. We saw the regular expression and the equivalent NFA. Now the other way around. Now, if this is my NFA, what is the equivalent regular expression? AB. Okay. And if this is the NFA, then what is the equivalent regular expression? Yeah. A union B concatenated with B. Exactly. It can also be written as sigma B. Here the assumption is sigma is AB. Okay. So like I said earlier, from a particular state, if you are having outgoing arrows, more than one outgoing arrow, that is like an OR condition. Similarly, if you have even one outgoing arrow with more than one label, that is also like an OR condition. Okay, so let's look at some more. What about this one? Yeah, A union B concatenated with A union B. That is, the first letter can be anything, A or B. The second letter can also be A or B. In other words, it is sigma concatenated with sigma or sigma square. Okay. Now, what about this one? B, A star B. A can come 0 or more times in between. Okay. What about this one? Yeah. So this is A union B, A star, A union B, or it can also be written as sigma A star sigma. Okay. Now, what about this one? Same thing. It doesn't matter whether you write the labels on the same arrow or two different arrows. It is like an OR condition only. Okay. Now, what about this? AB into AB concatenated with A union BA. AB star means it is A concatenated with BA star. So you can get an A. Once you get an A, then you are just getting BA, BA, BA 0 or more times. That's it. Quite simple. Or another way of writing it is AB whole star A. So here the idea is A is coming at the end. Here the idea is A is coming at the beginning. But both cases it is the same because it is ending with BA. You can think of it as A coming at the end or at the beginning. It doesn't matter. But this is more closer to the structure. This language is also identical with it, but this is more closer to the structure. You get an A and then you are constantly getting BAs. That's all. Okay. Now let's look at one more. What about this one?
A union BB concatenated with B.
Anyone else?
B star union BB B star.
Okay. Yeah, that's the same thing what she said. Okay. So what we will do, we will simplify it further. So this is A. Now what we will do, we will sort of compress this portion. And what will be the regular expression for this portion? Just this portion. It's just BB, right? So we will replace this with BB. Now it is easy. A union BB concatenated with B star, right? Okay. So the more complex machines you get, you need to sort of do it step by step. So condense some portion of the NFA into a regular expression, then condense some more portion, then condense some more portion. Finally, you will get one huge regular expression for the entire NFA. All right. So now let's look at a slightly complex example. Yeah. What about this one? This is not easy because there are many arrows and the arrows are, in this particular case, the start state as well as the final state themselves need to be condensed. In all the previous examples, the start state and the final state need not be disturbed. The intermediate states were condensed and we got regular expressions. Like for instance, you look at all these cases, in each of these cases, only the intermediate state is replaced. And like in this case, it became AB. You replace the intermediate state with AB. Here you replace the intermediate state with A union B concatenated with B, and so on. In none of these cases, the start state or the final state did not have to be replaced, right? But in this particular case, the start state needs to be replaced and the final state also needs to be replaced. Why? Because you can condense only that path which is a directed path. You cannot condense an undirected path. For instance, in this case, we are able to condense this path because this is a directed path. Both these arrows are in the same direction. If this arrow or this arrow were in opposite directions, like this arrow is in this direction, but suppose this arrow is in this direction, then you cannot condense that. Both of them are pointing in the opposite directions, then you cannot condense such a path. Only if both arrows are pointing in the same direction, that is a directed path, so you can condense the node which is only in a directed path. Okay, but in the next example, the final state is in a directed path and also the start state is in a directed path, whereas this state is not part of a directed path because this is pointing in this direction and this is pointing in this direction. So you cannot condense this. You have to condense this or this. But then if you condense either of these states, you are losing the start state or the final state. Okay, so to avoid such scenarios, what we do for any NFA in general, we add two more states, a new start state and a new final state with epsilon arrows to the previous start state and the previous final states. So we add a new start state with epsilon arrow to the previous start state, and we also we convert this to a non-final state and we add an epsilon arrow to a new final state. Okay, so now this particular entire machine can be converted into one single regular expression between these two new start state and end state. Okay, now you need not worry about condensing start state or end state. Now you have new start state and end states, so the entire remaining machine can be condensed into a regular expression. Okay, so that's not an issue at all. Now, so now we can condense, say this is a directed path, right? So there are two paths here. When suppose if I remove this node, then I will have actually two paths. Yeah. Sorry? You won't get the answer because it's a long one. Okay, tell me the answer quickly. B star, A, B star. You mean like this? BA? This entire thing? Or this one? Here. Okay. I need to check. We'll see. Because there may be more than one way, you may get more than one regular expression depending on which path you are condensing first. So if the order changes, the regular expression changes. So let's keep it aside for a moment. Okay. So if I remove this node, basically this node is a connecting node between this node and this node, as well as this node and this node. Okay, so there are two paths. One is this path, another is this path. Okay, so we'll get a regular expression for this path and we'll get another regular expression for this path. Okay, so let's see that. So this portion remains same. Like this portion we are not condensing, so this portion remains as it is, but this node we are removing. Okay, so now, so first let's look at this path. This path, when I remove this node, this path's regular expression will be A B star, right? A B star epsilon. Epsilon you can ignore in concatenation, so it will be A B star. No, it will be A B star because you are starting with in this direction. So A will come first, then B star will come. Order is important. So this path's regular expression will be A B star. And what will be this path's regular expression, the second one? You just follow the arrows. A, B star, B. So you will have another arrow, A, B star, B. Okay. Now before you condense any node, you have two arrows in the same direction between same two nodes. So you first combine them with what operation? If you have two or more arrows between same two nodes, you combine them with union, right? So this, so this is epsilon, this is B, this is AB star, and this will be A. Now this will be union of these two, that is A union A B star B. Okay. Now what is the next directed path? This is a directed path, right? So let's remove this node. Okay. So it will be so this top portion will remain same, B self loop and AB star. The bottom portion will be this expression concatenated with A, right? So it will be a self loop on this A union A B star B. This entire thing concatenated with A. All right. Now again we have two arrows, two self loops on the same node. So we combine both these expressions using union. So let me just copy this. Okay. Now it's a simple one. You remove this node, you put star on this and concatenate it with AB star, right? I remove this node. I remove this epsilon. So this entire expression whole star concatenated with AB star. Okay. So this, yeah. Someone asked. So finally, this is the regular expression equivalent to the given NFA. Okay, so it is so complex. You may get a different one if you take a different path. Maybe if you compress or condense the start node, you will get a different regular expression, but the process is similar. All right. So let's stop here.